Okay, so I'd like to get started with the overview of the class. This is from the syllabus, and we just have a brief description of the class, what we're trying to achieve. So the class Applied Process Simulation, it's going to be an introduction to simulating processes related to uh, fluid flow, through porous media, conduit tanks, so a variety of different kinds of fluid flow we'll be looking at. Transport of heat and mass, chemical reactions, and deformation. So I really think of it as a class where it's really reactive transport with deformation thrown in there. Usually deformation isn't included as something in reactive transport, although perhaps more so these days. But anyway, that's what we're going to do for the class. We'll look at each one individually, and then we'll see how these different processes are coupled together. Um, we'll look at how to kind of the basic overview, the concepts, how the analyses are done, and then we'll have a variety of applications that we'll be pulling from natural systems and from engineered systems. So the things that I hope you get out of the class in this kind of the big picture is that the first one is to take processes or things that you're interested in and translate it into numerical analyses. We're going to be doing lots of simulations, but in order for that to be interesting and meaningful, you have to be able to go from the processes, the actual processes, to numerical analyses that you might conduct. And then you need to be able to describe the mathematical basis for the simulation. So it's not just good enough to be able to translate it into numerical analysis. You kind of have to know what you're doing enough to describe it to somebody. So we'll be using software and simulators, and it's easy to get kind of lulled into using those as a black box. But one of the objectives that I have is that that won't be the case. That you'll have some grounding in the mathematical basis, and then we want you to be able to conduct numerical simulations of these processes and interpret the results for a variety of applications. So hopefully, I don't know, maybe on the last day of class we can go back to this and see how well we did. But that's the big picture. And so why do we want to do that? Well, I think there are a variety of reasons. Here are a couple of them. One is that if we can do these simulations, uh, it'll give us the ability to take a look at, we can do things like numerical experiments that will show us how these different processes behave, what are the controlling factors, and this allows you to train your intuition about how things work. So hopefully we can take the results of these simulations and integrate it into your intuition. The other thing is that you can test hypotheses. So you'll have some ideas about how something might work, and then you can do simulations that are based on physical and chemical principles, and they can tell you whether it would be possible for it to work that way. So that would be a scientific application, and then more of an engineering application would be related to design. If you have a system that you want to have work in a particular way, you can try out various options, see what might be working the best for the least cost. Doing numerical evaluations of designs is much cheaper and quicker than prototypes, and it's more comprehensive than analytical calculations, although analytical calculations are certainly a good place to start. So for engineering design, I think that the methods that we're going to be seeing in class this semester, they're becoming quite important. I think in the future they're going to become very important as a way of doing designs. They're really quite powerful techniques. Okay, so what's the strategy for success in doing this kind of a simulation approach? So this is kind of a big picture overview of doing numerical simulations analysis. Some of you had a class from me in the last semester, and it's quite similar to the approach that we use there. So we start off with some observations, maybe some hypothesis or design. This is a problem that you want to solve, and it has a lot of details, and maybe it's fairly complicated. So the way to success, though, is to take that problem, simplify it down into a more simple form, a conceptual model. It still, at this point, is qualitative, although maybe it has dimensions at this point. But it doesn't have real numerical results. And so the trick then is going to be to take these concepts and translate the concepts into the analysis. The analysis will then really be the basis for getting some numerical results. We need to take this translation, set the problem up, solve it, get some numbers, and then we need to have some skills at interpreting these results. And then, of course, when we're all done, we've got these results that we've determined, and we have to be able to express them so somebody else can understand what we've done. Okay, so that's the strategies for success, and we'll be doing a lot of that. Really, we'll be going through those whole steps. Although for the course, we're going to focus mostly on what I've circled here. Um, how you translate the concepts into analysis, and then this setting up and solving of the problem. That's where you need to have to do some numerical calculations and get results. So those will be a main focus, although we're certainly going to work on interpreting results and committing. We're going to work on all of that kind of thing. Okay, so one of the key aspects of this is translating the concept to the analysis. So you have some kind of ideas and you want to do a simulation of it. And so these are the things that we'll need to be looking at. Geometries, so this is the shape and size of the domain that we're interested in. The governing equations, these are the processes. And we might think of it as what kind of rules are being obeyed within the region. The boundary condition, this is more information about processes and rules, but on the boundary. The governing equations really are going to be internal rules for the processes. This is how things start out. And then parameters and dimensionless groups. These are these are aspects of the problem that make it specific to a particular material. So this would be, say, material properties. And then we might have some constraints or other requirements. So we got to figure all this stuff out, and then as part of the setup for doing this, we're going to discretize the geometry or create a computational mesh. So I'll show you more about this in just kind of an example way. The next step, though, after we've done the setup, is to solve the problem, and that's going to involve we'll use some numerical techniques to solve the problem. Hopefully, what we're doing, though, will be, as part of this process, will be quite clear that we're solving a mathematical problem, and then we'll obtain some numbers. So there'll be several things that we'll do with this. One of the questions we might ask in the beginning is, do the numbers solve the math problem? And so we'll use a numerical technique to solve these equations, and the numbers that we get, it doesn't necessarily mean that it's right. And so we'll want to have a way to check and see whether in fact we've obtained a solution to the problem. And so one way that we can do that is to compare our results to the exact results. And the strategy here is that for some cases we might have an analytical solution that would give us exact results. So comparing our results to exact results, that's a process of verification. And so that'll be one of the things that we'll do with the analysis. And the other thing is going to be, well, are these numbers really physically meaningful? So we can get some results, but do they really reflect what happens out there in nature? So this is called validation, and we'll validate results by comparing to data or some kind of observations. And then do the numbers represent reality? And what's going to be necessary there is to take the analysis, and typically what you'll do is adjust the parameters in the analysis so that you're matching some data. So it's similar to validation. We'll be calibrating models by adjusting parameters. So this would be to give a fit to data. So that'll also be one of the things that we're trying to do. Okay, so we've set the model up. We've we've got some results. We've got some numbers. We want to interpret those results. So what we need is to have some. We've got a bunch of numbers. We might put those numbers in tables. That could work. Often though, we'll use graphics. So we'll have some kind of a plot of the results. We might also do sensitivity analysis, where we systematically vary a parameter and see how the results change. We might vary a parameter and get a whole set of curves that look like that. So that's giving us a little more insight into how the system's behaving. And so these are the tools that we'll need to use to interpret the results. And then the last step, communication. This is really putting together what we've done and expressing it to somebody else. And so this is going to be a key aspect of all of this, because if we can't do this, we don't really get credit for doing the analyses. And if we don't get credit for it, then why bother? So to communicate the results, this is just a simple approach. You want to make sure to state your objectives. One of the things that I think sometimes happens when we're getting started is that you get kind of immersed in the details and you lose track of the objectives that you're trying to achieve. Usually these objectives are going to be that you're trying to get some insight into a particular problem or a particular system. The objectives aren't going to be that you need to get the homework done on time. That's not what I have in mind for objectives. You want to try to learn something. And then what I hope you guys can get is some practice documenting the methods that you've used. So this sequence of defining a problem, doing a conceptual model, numerical model, and then a solution. We need to be able to describe that, present results in terms of graphics, and describe what happened, and then extract some insights. What do these results mean? How do they meet the objectives? And what's the take-home message? So we'll be focused in on this central set of materials, but we'll also be working on some of that stuff there. Okay, so that's the overview. I'm going to stop this.